My friend and colleague, the late Jim Court, made up some yum worksheets for vectors. We'll treat some of his items here. Let's begin with the simplest, an iron ball suspended by a string. The red vector represents its weight, which we label W. To be in equilibrium, an upward force must act on the ball. That's string tension, which we label T. We draw the length of the vector as long as the W vector, but in the opposite direction. Both vectors add to 0. We draw the tails of the vectors from the center of the ball, where the dot is. Here's the same ball suspended by a pair of strings. We have the same weight vector. Since the strings are vertical, can you see that the tension in each string is half W? The two T vectors are half the length of the W vector. The sum of all vectors cancel to 0 and the ball hangs in equilibrium. Let's consider a pair of strings that are not vertical. Since the ball's at rest, tension vectors for both strings must combine to produce an upward vector equal and opposite to W. We draw it here with a dashed line, which will be the resultant of the tensions of both strings. Using the parallelogram rule, being careful to keep the sides of the constructed parallelogram parallel to the strings, we see that the two tensions are somewhat greater than half the W vector. If the strings are wider apart with a greater angle between them, will the string tensions also be greater? We go through the same steps as in the previous case, and what do we find? Yes, the tensions are greater. How about this arrangement? More interesting. We begin by labeling the W vector. We know both tensions have a resultant equal and opposite to W. That's this vector. So the parallelogram rule shows us, yum, here we see the tension in the left string is greater than W, and tension in the horizontal string is slightly less than W. The lowest string need not be horizontal. How about this arrangement? Even more interesting. As usual, the tensions in the two strings have a resultant equal and opposite to W. Note that our parallelogram extends beyond the walls, which is quite okay. This time we see both tensions are appreciably greater than the weight of the ball. Suppose the string breaks and the ball is in free fall. How many forces act on it? By the definition of free fall, no forces other than gravity act on it. So the vector diagram is simply the W vector, nothing else. But suppose there's air resistance. Then a force opposite to W builds up. Let's call the force due to air resistance R. We see the net force on the falling ball is W minus R, which means that acceleration is less than that of free fall. The ball doesn't pick up speed as quickly as it would in a vacuum. As the ball falls faster and faster, air resistance builds up, eventually, perhaps, equaling the weight of the ball. I want to leave you with a question. If air resistance becomes as great as the ball's weight, is the ball then in equilibrium? What do we say about its motion at this point? Think about that. Until next time, good energy.